This is going to be our last category of aqueous reactions called oxidation-reduction reactions. First of all, with oxidation and reduction, these are processes that basically have electrons being removed from one and then transferred to the other. So oxidation specifically, this is where substance loses electrons. Reduction is a process where they gain electrons. And of course, these little diagrams on here help you sort of remember them. Oil rig, where OIL, oxidation is losing electrons, reduction is gaining electrons. Or on the other hand, you have our friend Leo the lion, right? Leo, and then Grr, where losing electrons is oxidation, gaining electrons is reduction. Either way, they give you the same idea. The point is, this is effectively how you can keep track of what substances do what. This can involve ionic compounds, molecular compounds, elements, combinations of both, ions. It's a sort of a kind of a free-for-all. So it looks a little messy at first, but I think you'll find you get the hang of it and kind of focus on the parts that really matter. And of course, neither process can exist without the other, right? So I can't really have one oxidation without there be a corresponding reduction, because these electrons have to come from somewhere. They don't just come from thin air. They come from other substances that either gain or lose those electrons. A quick example of redox, right? We have salt formation, where if I take salt, sodium, which is a pure metal like here, a bunch of all pure neutral atoms of sodium. Chlorine is a gas, a bunch of little chlorine molecules floating around. When they combine, they kind of have this big old violent reaction. And that violent reaction, again, is the result of basically chlorines taking electrons from sodium. So the electrons are being transferred from sodium onto chlorine atoms. And again, there's a big old rearrangement, and now you get sodium chloride, which is a bunch of ions there as a result. So basically, we're talking about electron transfers, and not necessarily about ionic compounds, but the fact that you have new substances that have different electron arrangements. Another example of redox is combustion. This is a pretty important one. You guys probably recognize this, but right now, again, we'll talk about this later on. Right now, each of these has a certain number of electrons associated with them, but then after the combustion, right, after you allow it to burn, the new products again have their electrons rearranged. Now, for this one, it's not as obvious which ones necessarily have gained or lost electrons. We'll talk about that later. But that's basically effectively how you can approach these. You know that there's going to be some change that occurs, and because it's not obvious, you might not see it, but yes, there's definitely some electrons being moved around. Why exactly is redox so important? Well, many of our biochemical processes as living things definitely involve redox. So our friends such as ATP, NADP, DNA, these are all reduced and oxidized all the time as part of our normal functioning. And then, of course, photosynthesis, respiration, these are a lot of different types of reduced and oxidized substances. Finally, industrial applications. Many cleaners definitely utilize redox. For those of you who like to have clean substances, sometimes you might bleach it. That bleach makes there be some sort of electron changes, which is an example of redox. A lot of synthesis, meaning we're making things, generally require some kind of a redox to be able to produce substances that behave the way we want them to. And then, of course, things like cleanup spills or water reclamation, where you've had some bodies of water that have been dirtied over the years, and then redox can help clean it up. First thing we're going to learn about is something called oxidation states and oxidation numbers. Now, these are actually kind of something we've learned before. Some of you may remember them as charges. All right, now that's again a little bit of a misuse that we've been doing over the months. These are a little bit different. They're not exactly the same. So here's how it works. Since electrons are exchanged, it becomes vital to identify the oxidation states of each atom that are involved. Now, notice how, again, we're not saying necessarily charges, but specifically oxidation states. By the way, oxidation states, oxidation numbers, these two, again, are actually interchangeable. The word charges is a little bit more specific to just ions. This is like charges, but instead for covalently bonded atoms rather than just ionic compounds. And then again, there's some similarities and overlap that we talk about. So let's go and take a look at this next slide. This is, again, a pretty good list. You might want to commit this to memory. A pretty good list of what's going on. So first of all, different substances have different oxidation states. And there's some rules that we've found over the scientific sort of exploration to basically get some rules out. First of all, oxidation state of a single atom by itself. That atom by itself, again, is going to have an oxidation state of 0. For example, right? Like summary here, element 0. For example, you have sodium. Sodium is a pure element by itself. It is a solid metal that we saw previously in that when we made salt, right? It's a solid metal. That's going to have an oxidation state of 0. Regular old oxygen also has an oxidation of 0. O3, which is again ozone, that's a pure element by itself. That's going to have an oxidation of 0. And then mercury here on the end, also 0. So these are all pure elements, even though you have some that are diatomic or even triatomic, they're all 0. The next one, a monatomic ion is the same as its charge, meaning that the oxidation state of a regular old monatomic ion that we've seen before, that's going to be the same as its individual charge. Now, we've talked a lot about monatomic ions in the past. For example, sodium ion, right? Sodium ion has a charge of +1. We know that. But again, in this context of looking at oxidation states, oxidation state of sodium is also +1. Now, so there's probably some confusion as to why we even care necessarily that we apply a different term, and that's fair. But, in this context of reduction and oxidation, these oxidation states are much more useful. And it just so happens that it overlaps with the charges that we've already known. Same thing with chlorine, right? Chlorine, when it becomes the ion, it becomes chloride, right? This monatomic single atom ion has a -1 charge, so the oxidation state of chloride is also -1. Fluorine. Now, fluorine here is going to be one that's going to have its own little special case. Fluorine, the oxidation state of fluorine is -1 when it's in compounds. Okay, so in this case, right, if you look at HF right here, this fluorine that's in here, that atom of fluorine has an oxidation state of -1. And then PF3, right, same idea, because fluorine is in a compound, right, it's going to have a -1 oxidation state. Now, that kind of is also consistent with what we know before. That fluorine, if we look at a periodic table, it's in this group of the periodic table. So we know elements in this group, when they become ions, are -1s. And that's important. But also notice, right, we're talking about this being an ion. If I scooch back over here, this is not acting as an ion. These are nonmetals. These are nonmetals, right? Nonmetals don't have ions. These are for regular covalent compounds. And this, again, is where you kind of start to have this weird blend of where we use sort of the ionic sort of labels, like charges of +1, -1, so on and so forth, but for covalent compounds. So with fluorine, in this case, right, it has an oxidation state of -1. It would not be accurate to say that fluorine has a charge of -1. Oxygen. Oxygen is also kind of a funky one. Again, these are called oxidation states. So oxygen definitely has a big role in this, but let's go and see this one, how this works. Oxygen is usually -2. Right? So the oxidation state of oxygen is usually -2 in its compounds, with one example, and that'll be, or one, exception, which is our friend peroxides. If you remember that polyatomic ion, that's O2 with a -2 charge, where each oxygen instead is a -1 oxidation state. So your oxygen is a -2 oxidation state, pretty much across the board, unless you see it as a peroxide. So in our friend here, H2O, this one right here, it has an oxygen in it, right? It's not really a charged ion. It's a covalent molecule. Water is made of nonmetals, so it's a covalent compound, but we still have an oxidation state of -1. And then for CO2, same idea, right? Carbon dioxide. This is not one where it's a carbon dioxide where it's just an oxide ion, right? Remember, the oxide name gets applied to any covalent, second covalent element. And so this, again, it still has I'm sorry, I said the wrong thing here. This would be -2, and this should now be -2 as well. All right, so oxygen, again, is always -2 when it's in a compound, except for, again, as a peroxide. So please forgive that mistake earlier. In other contexts, right? If you do have something that was like, hey, sodium oxide, right, like that, right, sodium oxide, this is an ionic compound, right, this has a slightly different set of bonding characteristics. This oxide here would have a charge of, right, you have an Na+, you have a charge of, -2. Yeah, that's an ionic compound where that involves an oxygen ion, so an oxide. That has a charge of -2. So the oxidation state of this ion would also be -2. But again, that conclusion is a little bit weirder or harder to make if you look at this CO2. That's a covalent compound. There's not really charges involved. Yet, we still know that because of this rule, oxygen will have an oxidation state of -2. Finally, hydrogen. This one's pretty straightforward. Hydrogen is +1 in its covalent compounds, right? So we're not talking about plain old hydrogen when it's by itself as H2, right? That's always going to be 0 because that's an element. But if it's hydrogen in a compound, right? For example, H2O again, hydrogen is covalently bonded to oxygen. That's going to have an oxidation state of +1. Same thing for this one, +1, and that one, +1, because they're all part of a compound. Now, we can actually look at these and sort of figure out what's going on by doing some work. Now, like we said, those are the ones that we can guarantee, but you still actually might be asked about other ones that are not quite as obvious. Let's try this out. First of all, CO2. All right, here we go. This one says, assign the oxidation state to all atoms, CO2. Now, of course, normally we'd be going from left to right, but if you look at that list, carbon isn't on there, right? Carbon, there's no comment at all about carbon. It doesn't even fit in any of the categories. So instead, let's focus on the part that we do know, which is oxygen. So with oxygen, right, I know that oxygen's in a compound, so individually, right, it's going to have an oxidation state of -2. And this, again, kind of operates sort of like we did a long time ago when we talked about balancing charges in an ionic compound, but now we're talking about a covalent compound where that's not exactly the same thing. However, the logic is identical. Since I have an individual oxidation state of -2, I'm showing here that there's 2 atoms of oxygen. That means overall it has a -4 oxidation state that the oxygen provides. And that means on the carbon, right, because this overall thing is neutral, there's no overall charge or nothing else with it, this is actually going to end up being a +4 overall oxidation state. And because carbon, right, there's only one of those atoms, that means the individual carbon oxidation state is +4. So the question again is assign oxidation states. I can finally say carbon has an oxidation state of +4. Oxygen has an oxidation state of -2. What about SF6? All right, so let's try this one out. SF6, same principle, right? I don't know anything about sulfur, but I do know something about fluorine. If you look at the previous slide, fluorine, as it says there, in a compound always has an oxidation state of -1. And so, since there's 6 of them, you're going to have an overall -6. That means overall positive has to be +6. And since there's only one sulfur, we know that it's going to have an individual oxidation state of +6. So finally, as a summary, sulfur is a +6, fluorine is a -1. Right? Nitrate, this one is a little bit trickier. So this one has an NO3 -1 overall charge. Right? This is our first kind of overall ion that we have to deal with. Let's figure out what's up. Let's write it over here. So NO3 with a -1 overall charge. Now, this one's going to take a little bit of reasoning, so bear with me for a second. All right. Now, nitrogen, again, we don't know anything about, right? Nothing on that chart we saw on the previous summary page that's involved. But what about oxygens? I know that there's always going to be -2 overall. So -2, right, individually for oxygens, there's 3 of them. That means it's going to be overall -6 that the oxygens provide. What about the nitrogen side? Normally, again, we would just do +6, but again, that's assuming that the overall substance is neutral. This one is not, because there is still that -1 charge right there. So what does the positive side have to be if my -6 is here? So that overall it's -1, +5, right? So the +5 overall charge will kind of combine with the -6 +5 overall oxidation state. Will combine with the -6 overall oxidation state. +5 -6 gets you -1, which is the overall charge of nitrate. Great. That means finally, for a single nitrogen atom, since its overall oxidation state is +5, the single atom will be +5. So in summary, nitrogen will then be a +5 in this substance. Oxygen will be a -2 in this substance. So we're talking about individual oxidation states. Here's some more you can try out. This one's a little bit funkier, right? Talking about the oxidation number now of all atoms once again. But notice they're all nitrogen, nitrogen. So they're all some kind of a nitrogen-containing substance. And you'll see that, since we don't have a specific nitrogen kind of like pattern that we saw on that one slide, that summary chart, that summary graphic, you're going to have to do a little bit of work. Some of this kind of is almost going backwards. All right. So let's finish this off by talking about reducing and oxidizing agents. When it comes to reducing and oxidizing agents, you basically are going to figure out which one is doing the reducing, which one's doing the oxidizing. All right, so this one's going to take a couple of little bits of work. First of all, in any redox reaction, it's important to identify the substances that are undergoing the oxidizing and the reducing. Also, we need to identify, again, this term agent. So this is, again, an agent of change. This is the substance that's doing it. So the reducing agent is a substance that causes the other substance to reduce, right? So the reducing agent is causing something else to reduce, but itself is oxidized. Okay, that's a lot. Let's try this next one. So oxidizing agent, its counterpart, the substance that causes the other substance to oxidize itself is reduced. Oh boy, okay. At this point, it starts to get really, really easily turned around, but let's try this out. I'm going to go ahead and kind of point out this diagram on the bottom, or this reaction at the bottom, and see what's up. They've already identified the oxidation states for each of these substances. All right, so let's kind of try this out. First of all, H4, so hydrogen anyway, they've already told you that it's +1. We know this is one that we know. Right? Hydrogen's always going to be +1. There's 4 of them. Carbon, therefore, will have an oxidation state of -4. Oxygen right here, this is a pure element. oxidation state of 0. CO2, we kind of just did this one earlier on the previous page. That's going to be -2 for each oxygen, right? +4 oxidation state for carbon. And then for water, same thing. Oxygen is a known -2. Hydrogen is a known +1. So those are the labels that you see there. Now the next part then is something we haven't done yet, but this is worth pointing out, right? So this is a oxidation-reduction reaction. How do we know it's a redox reaction? Redox, reduction, oxidation. How do we know it's a redox reaction? Because the oxidation states change. Right, so let's take a look at our carbon. Carbon starts off as a -4 over here. So I'm going to draw an arrow going from the carbon from here to here. Right, it goes from a -4 to a +4. How does it do that? How exactly does it go from -4 to +4? Well, again, that's because some electrons get moved around a little bit. To go from a negative to a positive, what happens to the electrons? We lose electrons. That was a terrible word. Lose electrons. There we go. Which means what process occurred? That means it is a reduction, right? Nope, just kidding. It's going to be oxidation. Right? Oxidation is losing electrons. Because we lose negative electrons to go from a negative to now a positive oxidation state. All right, what about some other stuff? Well, hydrogen, right? Hydrogen's +1. What about over here? Hydrogen, well, if you look at it over here, again, hydrogen's still +1. So, that one didn't change much. We can kind of leave that one alone. What about oxygen? Well, oxygen starts off at O here, right? And then what do you notice over here on the right side is that you have oxygen here in this substance, oxygen here in this substance. What we notice about their oxidation states, they're each -2. So in this case, I'm going to kind of do this, sort of cram it in there, but going from here over here to this oxygen and also to this one, because it happened to both of them. What happened? Well, it went from 0 to now -2 for both of these, right? And so that means in order to become more negative, you end up gaining electrons. And that means this underwent reduction, red, right? Kind of sort of oxymoronic with the color. But yeah, this is the meaning that they gain electrons to undergo reduction. So oxygen to go from 0, -2, -2, and gain electrons. And so that's again worth noting, right? So the process that carbon underwent to go from here to here, that's going to end up being the oxidation process, whereas oxygen undergoes reduction. And then finally, right, that's where we need to get into this discussion about reducing agent and oxidizing agent. So these effectively are referring to the reactants. So what are the reactants? Reactants. Just didn't really feel like writing that word out. So which one of these reactants, of course, then can you label as the reducing agent? Which one of the reactants can you label as the oxidizing agent? Right? These are the things that are causing the other substance to do something. So when these, again, electrons right here are lost from carbon, they go somewhere and they go to the oxygen, right? So there's that relationship between these substances. So as it turns out, we can basically say that our friend here, because CH4, right, the substance that's involved, CH4, especially the C, this will serve as our reducing agent. How do we know that? Because the reducing agent is a substance that causes the other substance to reduce. So the other substance here is reduced, right? Is reducing anyway. And therefore itself is oxidized because itself is losing electrons. So there's kind of like a double sort of catch here. It's kind of strange. You say that something that is undergoing oxidation is called the reducing agent and causes the other substance to be reduced. On the other hand, you have our friend O2, right, oxygen. This one, again, is undergoing reduction, right? So as it undergoes reduction, it actually causes the other substance to then oxidize. So O2 here, right, this would be considered our oxidizing agent. This thing, again, is the one that undergoes reduction, right? So itself is reduced, and it causes the other substance to undergo oxidation. So we call O2 our oxidizing agent. Kind of consistent, or kind of at least somewhat some consistent, because you do have oxygen being the oxidizing agent. All right, and that'll do it.